So thanks, Antonio, for the invitation. I am very glad to be here. Okay. And so my talk will be about the application layer in the open architecture that Maria just presented, and on the application support for in the fog environment. So in particular, I will talk about data streaming application, which are a particular kind of application in the big data area, where we need to we require to process a continuous flow of unbounded data that are generated by multiple and distributed sources. And so the idea is to, of course, extract valuable and reliable information from these data in a timely manner. Of course, we have now a variety of low latency and location-aware application in diverse domains. For example, think about situation-aware application. For example, in the intelligent urban transport, there was a project, a European project, for example, that had a use case in the city of Dublin, and they through data streaming application, we're able to change on the fly the route of the buses in the city. And you can also think about application related to surveillance, fraud, traffic congestion, and of course, social data mining. And when you analyze the useful frameworks that are available in the open source community for data stream processing, you can see that all these frameworks have been designed to operate in a data center. And so they do not carry into account, they do not consider the latencies among the processing nodes. And so our idea, which is a common idea for the fog environment, is to increase scalability and availability of the application, to reduce the latency, to reduce the network traffic, and to reduce the power consumption. Our idea is to exploit fog computing, to have the processing related to the data streams on many micro data centers which are located at the network edges. So no longer in a single data center. And of course, these new scenarios pose to us many new challenges because we have to consider that the processing nodes have latencies that cannot be neglected. And we have to consider also that the computing nodes and that the networking resources are heterogeneous, and also that we can have business constraints, we can have capacity limits, and so on. And also, we have to consider that both the computing and the networking resources are not usually always available, and so we have to support mechanism for fault tolerance. And of course, we have also to consider that data cannot be processed everywhere because, for example, for privacy concerns. And so the goal of my talk is to give you a flavor of some of the challenges and some of the possible solutions that we have studied in the last 2 years that arise when we try to deploy a data stream processing application in a fog environment. And so just to give you some simple basis of what a data stream application is, we consider that a data stream application is a network of operators that are connected by data streams, and there is at least one data source and one data sink. And usually the application is represented by a direct graph, which can be acyclic or not, where the graph vertices are the operators and the graph edges are the data streams. And the operators are the processing elements that transform one or more input stream into another data streams. And each operator can be stateless or can be stateful. That means it has a state that used for the computation. For example, a filtering operator is a stateless one, while a counter is a stateful operator. And of course, stateful operators are more challenging when you have to migrate or you have to replicate them. And so the first challenge I want to present you is related to the operator placement. That means we have our graph on top that represent our DSP application, where we can see the operators and the data streams. And we want to assign the operator on the available computing nodes which are distributed in a fog environment. And so, of course, this is not a new problem. It's an old problem because it's in the area of scheduling. But in the fog environment, we have new challenges. And so our first work on this issue arises when we observe that current data stream processing systems, for example, Apache Storm, Apache Flink, or Heron, which is the latest data stream processing system released by Twitter, and we observe that they are all designed to run in a single data center. So they do not consider the latencies among the processing nodes. So our initial goal was to extend Apache Storm, which is the most used open source data stream processing framework in the research, so that Storm can now operate in a large-scale distributed and heterogeneous environment. And so in this figure, you can see the main components of our distributed Storm, where in red and blue, you can see the new components that we added to Storm. That one, Nimbus, is the scheduler, which is centralized in Storm. And the other nodes are the computing nodes of the system. And the worker is the minimal entity on which each operator can be assigned. And in this architecture, we added some monitoring capabilities, and we also added the possibility to have a distributed scheduler. And as regards the monitoring, our goal was to provide an estimation of the network latencies. Because we need to provide an estimation, an accurate, but not causing a significant overhead on the system, estimation of the network delays between each pair of nodes in the system. And so our idea is to use a network coordinated system. I don't know if you are familiar with some of them, but in this specific case, we use Vivaldi, which is a well-known network coordinates algorithm. And the idea of Vivaldi is to map the network, the nodes on a plan, and to measure the latency between the node as the distance between the nodes. And Vivaldi is a decentralized algorithm which is based on a gossiping scheme. And so it generates low traffic. And in addition, it can arrange modify the position of the node so that error can be minimized. And so once we put in place all the mechanism to have a placement policies in a distributed environment, we studied the literature. And as you know, the operator placement is an NP-hard problem. And, but we realized that in literature, for data streaming application, most works propose heuristics that address the placement problem. But all these heuristics have different assumptions. For example, they consider a different system model, they consider different application topology, they consider different QS metrics and attributes. Usually they have different objectives, and so they are not easily comparable. So our idea was to propose to study an optimal solution for the DSP placement problem, and we propose what we call ODP, which is the optimal DSP placement. It's a centralized policy, so to place the operators and the streams on a distributed environment, and we have formulated this problem as an integer linear programming problem. So of course, our goals was were to calculate the optimal placement, but we wanted also to provide a unified general formulation of the placement problem so that we can also compare different heuristics that have been proposed in literature. And also we wanted to consider multiple QS attributes for the application and the resource. Now I will give you a brief idea of the formulation of the problem without going into the details. So of course, first of all, we have to model the DSP application, and we have to model the computing and network resources. So for each, for the DSP application, for each operator, we have to model the computing resources that nodes that operator requires, and we have also to we also model the execution time per unit of data. And as regards the data stream, we model the data rate from one operator to another. And as regards the computing and network resources, we consider the amount of resources, the processing speed, and the resource availability. And as regards the network links, we model the delay from one node to another, the bandwidth from one node to another, and the link availability. And the decision variables of our problem are, of course, where we can map the operators and the data streams. So we have the X variables to map the operators, and we have the Y variables to map the stream on a network link. And I said before that we consider different QS metrics, and for example, we consider latency, which is defined as the maximum end-to-end latency delay between the data sources and the data sinks. We consider the availability, we consider the latency, the bandwidth, and the overall cost to manage the application. And this is the overall formulation. Without going into the details, here you can see the latency of the application, where the first term of the sum is related to the computing nodes, and the second term of the sum is related to the network links. Here you can see the availability, And again, the first term of the sum is related to the availability of the nodes, and the second term of the sum is related to the availability of the network links. Here is the network bandwidth and the capacity constraints, and here we have the assignment and integral constraint. And in the formulation of the objective function, we use tunable knobs so that we can easily set the optimal placement goals. And so we can use our formulation, of course, to determine the optimal placement, but also as a benchmark to evaluate existing heuristics that have been presented in literature. And so we implement our scheduler into Storm, and all the software we have realized is available on our website. And here you can see a simple example of using our problem formulation to compare the performance of the optimal solution to that of a decentralized algorithm, a well-known one in literature, that was proposed by Pisa and his colleagues at Imperial College. The algorithm by Pisa is a decentralized algorithm. It's an heuristic, and its goal is to minimize the elastic energy of the system, because they model the system as a system of springs. And so in this case, the lower the curve, the better is the performance. And so you can see that our optimal solution is the curve in red, and the algorithm by Pisa is the curve in green. And you can see some vertical lines on the bottom of the figure, and they are a reactivation of the distributed schedulers because of the errors in the latency estimation. So you can see that, of course, there is some instability in the behavior of the algorithm, and there is no change in the system environment. And we also realize two other heuristic algorithms that were proposed in literature, and so our approach can compare these heuristics with the optimal solution. And as I said before, we can easily tune the optimization goal to consider different utilities goals. So the second challenge that I want to consider, and it's an important challenge, especially in a fog environment where the environment can easily change, is related to the fact that data streams can generate a highly variable workload. And an easily, a common approach used also in data streaming application is to exploit data parallelism by replicating the operator so that we can manage a higher workload. And so each operator can be replicated, and the traffic and incoming traffic can be split between the multiple copies, and then the result can be merged. And so we studied again the literature and find that there is no solution to provide a joint formulation that take care of placement and replication concurrently. You have also to consider that most all open source framework for data stream processing do not provide any automatic mechanism to determine the optimal replication degree for each operator, but they require the user to manually tune the replication degree for each operator in the application. And so our idea was to provide a unified formulation that can jointly determine the placement of the operators on the system and the replication degree for each operator. And so we can determine the replication degree, and then we can place the overall application with the replicated operators on the distributed computing platforms that we have. And so we propose a new optimal problem formulation that we call ODRP, which is optimal DSP replication and placement. And again, now we have a formulation as an integral linear programming, which is more complicated than the previous one because we had to use multi-sets to model the new situation of replication. And I will not go into the details of the formulation. You can find it on a paper. We first had a workshop paper, and then we have a journal paper on this specific issue. And just to show you some results, which are taken also in this case using our Storm-based prototype. In this case, we also use a real application. The application you can see on the top is the solution to the grand challenge organized in the ACM conference on distributed and event-based systems, DEBS, in 2015. And in this case, the challenge, the first query of the challenge was to identify the 10 top, the most popular and most convenient path for the taxis in the city of New York. And here is the basic application where no operator is replicated. And our problem formulation can determine, on the basis of the source data rates, the optimal degree of replication for each operator. And in the graph, you can see a comparison of our solution that considers also replication, which is the one in blue, and the previous solution, which only considered the placement without replication. And of course, when the source data rate increases, the solution which considers only replication cannot scale, and the response time grows exponentially. The scale here is logarithmic. While our new solution, which also considers replication and then placement, is able to provide a stable response time for the user, and so to provide QS guarantees. The third and last challenges I want to consider is the challenges that we are currently working on, is to how to modify at runtime the deployment of the application, considering that many factors can change at runtime, because we can have load variation, because the data source can change, the input can change, the quality of service of the resources can change, the cost of the resources can change. For example, think about dynamic pricing schemes, for example, that we can have in also in cloud environments. The network characteristics can change, and we consider that some processing can also be performed on mobile nodes, we can also consider that the position of the nodes can change. And so the question is how we can adapt the placement and the replication when such changes occur. And so the common solution is to exploit a self-adaptive deployment. And well-known solution, which is derived from the autonomic computing idea of launched by IBM in 2003, is to organize all the overall architecture according to the MAPE reference model, where we have a monitoring, we have the analysis, we have a planning, and then in the planning we determine which are the changes of our plan, and then in the execution we change our system so that the new plan can be used. And for the data stream processing application here, we want to focus on how we can reconfigure at runtime the application deployment. And of course, the challenges here are that the replication cost should be considered because they can affect negatively the performance in the short term. How can we reconfigure a data stream processing application? We can migrate an operator from one node to another, or we can scale in or out each operator so that we can increase or decrease the number of replica of that operator. But this is not easy for stateful operator, because in stateful operator we have a state. And so we have to migrate the state, or we have to divide or to merge the state in case of scale out or scale in. And so when the current data stream processing framework perform operator migration or scaling, they freeze the application. So they stop the execution of the application. And so we have this freezing time that causes some unavailability of the application. And so we have to perform reconfiguration only when it is needed. And of course, we have to take into account the overhead for migrating or for scaling our operators. And so first of all, we studied Storm, and we realized that Storm doesn't have any support for migrating stateful operators. So we introduced into Storm some mechanism that can allow us to migrate stateful operators. And basically, we added a distributed data storage system where we can copy the state of the operator, and we can then retrieve the state of the operator once the migration or the copy of the code is completed. And using this mechanism, we propose a new formulation for an optimal problem that can also manage at runtime the elasticity of DSP application. And in this new formulation, we also consider the reconfiguration cost. So the costs which are related to migrate or scale in or out the operators. And again, here we formulated the problem as an integral linear programming problem. And without going into the details of the formulation, just to show you some results, which are based on our prototype on the same application taken from the DEBS Grand Challenge related to the taxi in the city of New York. On the top, here you can see the response time, which is the curve in dark, and you can see in red the change of the input data rate. And so we have an increase and then a decrease in the input data rate. And the small curve, the line here in our pink and in blue are the scaling and migration. And this is the QoS on the response time. And you can see that our solution that takes into account the reconfiguration cost and the reconfiguration penalties minimize the number of scaling and the number of migration. On the other hand, in the bottom figure, you can see the solution where we do not consider the reconfiguration penalties. And so the system is much more reactive. You can see a larger number of scaling and migration operation. You can wonder why the data rate has these strange patterns. This is because Storm, when a scaling or a migration operator or a scaling or a migration operation is done, freeze not only the application, but also the data rate. So the data rate goes down and then again up after the freezing state. And so using the reconfiguration penalties, we can have an availability which is more than 95%, and without using the reconfiguration penalties in the model, here you can see that the availability goes down to 81%. And so, of course, there is a much more future work to be done. Of course, the formulation now we have so far are for integral linear programming formulation, so they are NPR'd and they do not scale when we consider larger problem instances. So we are now working on efficient heuristics, and some of them we have writing a paper with some of them. Then a second possible solution to deal with runtime deployment is to deal with uncertainty into the model. And so to take uncertainty of parameters into account and to design robust placement algorithms. As far as I know, there are no robust placement algorithms in the data stream processing area so far. And of course, you can use these robust placement algorithms where when the changes are limited, and then you can integrate these robust placement algorithm with a reconfiguration to deal with more important changes in the parameter. Then so far we have studied only the placement of a single application, but of course you can consider the placement of multiple competing applications, and especially in a fog environment. Then another interesting direction could be to integrate the placement decision with software-defined networking, because with SDN we have the network loop, we have the network into the control loop, and so we can think about changing the path used by our network. And then another interesting topic would be to study cross-layer strategies that involve multiple big data frameworks in the fog environment. If you think, for example, about Heron, which is the latest data stream processing framework released by Twitter, also Storm was released by Twitter, but then they realized that Storm has some intrinsic scalability problem, and then they realized this new framework, which is Heron. But Heron doesn't work alone. Heron works on top of a scheduler, which is Apache Aurora, and Apache Aurora works on top of Mesos. I don't know if you know Mesos. Mesos is a cluster manager for managing multiple concurrent frameworks, for example, big data frameworks on the same cluster resources. So the problem here is that all the stack is designed for a single data center. And so you need to introduce a mechanism to take into account information about the network, to have this kind of stack operating for computing environment. Okay, so thanks for the attention. And I also to acknowledge the work all the works I presented is done with my co-authors, Vincenzo Grassi, Francesco Lopresti, and Matteo Nardelli at the University of Rome Tor Vergata. Thanks.
I have two small questions. The first one is more a clarification. In the first part of the talk, you described a static placement policy, okay? So you know some operators of your application and you have to decide how to map them on nodes, for instance, mobile devices, small devices of a fog system. In this case, you know that some operators are stateful and other are stateless depending on the application. Do you take into account the size or the estimated size of the state in order to decide the policy? Because this is not clear in the presentation.
We also include the size of the state, and we model, but not in the first part.
Okay.
Okay, in the first part where we have the static deployment, we do not take into account the size of the state. We consider the size of the state only in the last formulation that I briefly sketch this one. Because here we have to migrate or we have to distribute the state.
Okay.
So in this case, we also model the size of the state.
Okay. And then the second point is in the second part of the talk in which you described the more dynamic policy, okay? In this case, do you take into account the overhead of reconfigurations?
Yeah.
Okay, and how do you use this overhead in your problem formulation? How can you estimate this overhead, first of all?
Okay.
Because this is critical, especially for stateless operators.
Okay.
And how you use it in the model, in the
okay,
data.
we consider a reconfiguration penalty in the objective function.
Okay.
And then we model the reconfiguration cost in the formulation. And we consider the reconfiguration cost for migrating and for scaling. So for migrating, we consider that we use a distributed data storage where we have to copy the state and then we have to retrieve the state. And then we consider also that when we have migration or scaling, we have also to replicate the code of the operator, not only the state, but also the code. Yeah. So we model both stateless and stateful operator. And we also consider for scaling in or scaling out that we have to redistribute the state. So we have to divide the state, or we have to merge the state for a scaling in operator.
Also, I think that in the cost model of the reconfiguration, probably this cost model definition depends on the framework that you are considering. Because if you think that the computation, the whole computation is blocked until the reconfiguration is complete, this is a cost model. Otherwise, you have to change.
That's an issue because all the open source frameworks freeze the application.
This is a common...
So there is also, it's a common problem. So there is also space for changing the frameworks so to have reconfiguration which is more cheaper.
Efficient.
Yes, more feasible.